It begins like a whisper from the edge of the universe, faint, fragile, almost easy to dismiss. Just a smear of distant light, a tiny distortion in a sea of stars. Yet within that unassuming flicker lies something that should not exist, something so impossibly large that it bends the limits of what our universe is even supposed to allow. As we drift through the silent darkness of the cosmos, the camera glides toward that pale glimmer, letting it swell slowly, impossibly into view. What starts as a speck becomes a continent of stars, then an ocean, then a roaring, luminous empire stretching farther than the imagination dares. For a moment, the universe feels still, as if even the laws of physics pause to reconsider themselves. This is the first encounter with the galaxy that will come to redefine cosmic limits. A structure so enormous that its gravity shapes space like a sculptor shaping clay, twisting light around its mass, sending ripples through the cosmic web. Its sheer scale is overwhelming, hundreds of billions of suns woven into a colossal architecture that spans distances we can barely comprehend. It stands in silent defiance of everything astronomers believed galaxies could be. We drift closer, and the galaxy's spiraling arms unfurl like ancient cosmic wings. Each one is studded with clusters of blazing blue giants, dying red titans, and newborn stars set ablaze in shimmering nebulae. These glowing arms sweep outward like rivers of fire stretching across millions of light years. Yet even this stunning beauty carries a quiet threat. Nothing this enormous should have formed so early in the universe, not this quickly, not under the rules we thought governed cosmic evolution. The deeper we look, the more unsettling it becomes. The galaxy pulls us in, not just visually but intellectually, emotionally, a gravitational force made of pure mystery. It forces us to confront a startling possibility. Our understanding of the universe, so carefully built over decades of research, may be incomplete or fundamentally flawed. The discovery of such a massive structure is not simply a scientific surprise. It is a challenge, a provocation from the cosmos itself. Imagine standing on the ridge of a vast canyon on Earth, one so deep and wide that it makes you feel smaller than a whisper. Now stretch that feeling across billions of parsecs. That is the scale of the awe this galaxy commands. Yet the awe is mixed with something else, an instinctive unease, a sense that we have stepped into territory where our cosmic maps end and the unknown begins. Astronomers first saw it as a puzzle, then as an anomaly, and finally as an outright contradiction, an object that should not be able to exist at this stage in the universe's lifetime. According to everything we thought we knew about cosmic timelines, galaxies of this size take billions upon billions of years to grow through mergers, accretion, and slow gravitational choreography. But this one seems to have reached colossal proportions far earlier than any model predicts. Its age and size sit side by side like two mismatched pieces in a cosmic jigsaw puzzle. As the scene widens, we glimpse the galaxy's full silhouette against the cosmic night. It dominates the emptiness like a titan rising out of deep space. Surrounding it is a halo of dark matter so vast and diffuse that it stretches beyond the visible glow. This invisible envelope acts like a ghostly cocoon, shaping the galaxy's destiny while remaining untouchable and unseen. Even for astronomers accustomed to the strangeness of the universe, the sight of such a massive structure sitting so silently in the void feels like an unspoken riddle. The narration deepens, pulling us into the tension between what the universe shows us and what our theories insist must be true. The galaxy becomes a symbol of defiance, a monument to the unknown forces that shaped the early cosmos. Its presence asks questions in a language older than stars. How did it form so quickly? What processes allowed it to gather so much mass? Why does it seem so different from the galaxies we know? Each question increases the sense of suspense, as if we are standing at the edge of a revelation that refuses to reveal itself. And yet, beyond all the data and equations, there is something profoundly emotional in the encounter. The way the galaxy glows like a lantern hanging in the dark. The way its colossal arms spiral outward with both elegance and violence. The way it challenges us, not with hostility but with quiet, immovable truth. It is a reminder of how vast the universe is, how young our understanding remains, and how much still waits beyond our scientific horizon. As we drift even closer, the camera sliding past swarms of stars and luminous clouds, the galaxy seems to pulse with ancient life. It feels less like a structure and more like a living organism, full of tension, memory, and scars. We pass regions of intense star formation, violent storms of creation, and pockets of eerie stillness where ancient stars burn with the dim, tired glow of cosmic elders. Every new detail sparks a deeper sense of wonder, and deeper confusion. This galaxy structure is too clean, too complete, too advanced for its age. It is as if the universe skipped steps, as if some unknown process accelerated its formation far beyond what physics allows. The section ends on that unresolved tension, the lingering contrast between awe and impossibility. We have seen a giant unlike anything before, beautiful, terrifying, breathtaking in its scale, and yet its greatest mystery remains untouched. Not what it is but how it ever came to be. The question hangs in the cosmic silence like a distant echo, promising that the deeper we search, the stranger the truth may become. It began not with a blinding revelation, but with a set of numbers, quiet, ordinary, almost insultingly simple. A faint signal buried inside a routine survey scan, nothing that would make an astronomer sit up in their chair. Yet hidden in that data was the whisper of something absurdly large, so far beyond expected ranges that the initial reaction wasn't excitement but suspicion. Instruments malfunction. Algorithms drift. Noise pretends to be signal. Everyone knows this. And so, when the first measurements hinted at impossible mass and scale, the reaction was the same everywhere. This must be wrong. Picture a small research room lit only by the glow of computer monitors. Sleep-deprived scientists scroll through spectral lines and photometric curves, eyebrows tightening as the anomaly refuses to disappear. The numbers don't wobble. They don't shift. They remain stubbornly consistent. And consistency in science is the first sign of trouble. The more the data held firm, the more a strange tension filled the room, a mixture of curiosity, fear, and the electric charge that comes when something familiar begins to crack open. The galaxy wasn't even the main target of the survey. It sat quietly on the edge of the observed field, almost like it was hoping to remain unnoticed. Its light was stretched thin by unimaginable distances, arriving after billions of years of travel, weakened but still honest. The telescope reading it had no reason to lie. And yet it seemed to be telling a story that contradicted every rule of galactic formation astrophysicists trusted. The first person to flag the anomaly thought the brightness curve was miscalibrated. The second thought the redshift was misread. The third believed something was wrong with the filtering algorithm. Each scientist approached the data with skepticism, scanning for the glitch that would make everything make sense. But instead of falling apart, the galaxy grew larger, clearer, more defined with each correction. Instead of shrinking under scrutiny, it expanded. Numbers ballooned. Mass estimates rose. Star counts grew monstrous. The realization came slowly, like dawn pushing against a night that doesn't want to end. The galaxy wasn't an illusion. It wasn't a smear of overlapping objects. It wasn't a camera artifact or a cosmic coincidence. It was real. And if it was real, then the universe had a problem. At first, the scientific community reacted with caution. Claims of impossibly large galaxies had surfaced before, each one eventually debunked, explained away, or reduced to something ordinary. But this one resisted every attempt to simplify it. Its scale was too consistent across readings, too robust across wavelengths. The more telescopes turned toward it, the more undeniable it became. Radio data confirmed its mass estimates. Infrared imaging revealed sprawling star clusters. Spectral lines indicated staggering gravitational cohesion. It was as if the galaxy was stepping forward out of the cosmic shadow, daring the world to acknowledge its enormity. In meeting rooms around the world, teams gathered around projection screens showing the faint shape of the object. Discussions grew heated. Some insisted the data must be flawed. No galaxy this large should exist at that redshift. Others argued that the universe was simply surprising us again. If the data is consistent, then the data is right. A quiet few simply stared, overwhelmed by the thought that they might be looking at the most massive galaxy ever discovered, one that formed faster and earlier than anything in cosmology allowed. The tension between disbelief and wonder became a defining feature of the discovery. For some, the galaxy represented an opportunity, an exciting challenge that might push astrophysics into a new era of understanding. For others, it was a threat, a renegade structure that undermined decades of carefully built models. The psychological divide was stark. Hope versus fear, curiosity versus caution, possibility versus established order. As the object slowly transitioned from an anomaly to a verified candidate, a strange emotional shift began to ripple through the community. Scientists who had once dismissed the initial findings now felt a growing sense of awe. There was something humbling in realizing that the universe still had the power to surprise us so deeply. Something thrilling in knowing that a single galaxy could force humanity to reconsider everything from dark matter distributions to early universe star formation limits. The deeper the data analysis went, the more the galaxy revealed its contradictions. It was too massive, too bright, too evolved for its cosmic age. Its stars were older than they should be. Its structure was too mature. It had the gravitational presence of something that should have taken billions of years to assemble, yet the universe itself wasn't old enough at the observed redshift to allow that kind of growth. It was like finding a fully grown ancient tree in a forest that had only sprouted saplings moments earlier. Something didn't add up. Something fundamental was missing. The galaxy's existence wasn't just unexpected. It was impossible under the rules we thought governed cosmic evolution. The more the galaxy resisted explanation, the more its presence began to feel like a challenge thrown down by nature. Astronomers weren't just studying an object. They were confronting the boundaries of human understanding. Scientific papers began circulating quietly, filled with sentences like, anomalous mass estimate, unexpected structural maturity, and requires reconsideration of early universe formation models. But beneath the technical language was a simple truth. This galaxy was breaking the rules. Imagine the moment when the full composite image was assembled, a mosaic of data from multiple telescopes stitched into a clear picture of the Titan. The room goes silent as the galaxy materializes on the screen, not as a faint blur but as a sprawling empire of stars. No one speaks. No one needs to. The significance hangs heavy in the air. There it is. The impossible. The contradiction. The giant that should not exist. And somewhere beyond the data, beyond the glowing arcs and dark matter halos, lies the central mystery. How? How did something so massive appear so early? How did it gather so much matter so quickly? How did it grow into the largest known structure when the universe was still young and chaotic? The section ends with that unanswered question echoing softly through the narrative. The data is real. The galaxy exists. And with every new reading, the mystery deepens. What started as a line of numbers on a screen has become a cosmic revelation. One that refuses to be ignored, and one that hints that the universe is far stranger, faster, and more powerful in its creation than we ever imagined. The universe has rules. Invisible, relentless, immutable rules that govern the dance of matter and energy across the vast cosmic stage. Gravity pulls, light bends, stars ignite, and galaxies swirl in patterns that repeat over billions of years with elegant predictability. Scientists have spent centuries decoding these laws, turning them into equations, simulations, and models that can forecast the growth of galaxies, the collapse of stars, the expansion of the cosmos itself. We have built a framework, a scaffolding of understanding that makes the universe feel orderly, predictable, almost comforting in its precision. Yet then comes a discovery that shatters that delicate order, a galaxy so massive, so anomalously evolved, that it reads like a cosmic rebellion against the very rules we thought were unbreakable. This galaxy, stretching farther and holding more mass than any known counterpart, becomes a stark contradiction. In physics classrooms, we teach that galaxies form gradually, born from small clumps of gas that merge over millions or even billions of years, growing steadily as gravity orchestrates collisions, accretions, and slow accumulation of dark matter halos. Spiral arms unfurl only after long periods of gravitational sculpting. Central black holes grow steadily, feeding on nearby matter. Stars ignite in predictable cycles. But this galaxy ignores the timeline entirely. It appears fully formed, sprawling, and complex at a stage in the universe's history where, according to every simulation and every calculation, such grandeur should be impossible. The tension is cinematic in its drama. The orderly rules of the cosmos, painstakingly mapped over centuries, confronted by a giant that refuses to play by them. In this moment, the universe seems less like a predictable clockwork and more like a storyteller with a penchant for mischief, tossing a riddle into the lap of humanity. Gravity, which normally acts as both artist and jailer, shaping matter into elegant forms while constraining it, here seems to have been overridden, stretched, or accelerated beyond anything our models can predict. Every new observation compounds the paradox. The galaxy's density, its stellar population, and the mass of its central black hole suggest that not only did it form faster than expected, but it grew with an efficiency that challenges fundamental principles of astrophysics. Cosmic rules that dictate cooling rates of gas clouds, angular momentum retention, and star formation rates all appear inadequate to account for what we now observe. The galaxy's existence whispers of hidden forces or unknown processes that have allowed it to skirt, bend, or even break the rules that govern the rest of the universe. Contrast emerges naturally in this story. On one side, there is the universe as we thought we knew it. Predictable, explainable, constrained by logic and equations. On the other side, this anomalous galaxy, a gleaming leviathan, sprawling and complex, refusing to be explained, daring scientists to confront the limits of their understanding. The narrative tension is visceral. Curiosity wrestles with doubt, wonder collides with fear. There is awe in witnessing its beauty, but unease lingers, a subtle fear that our cosmic assumptions might be fragile, incomplete, even dangerously naive. The galaxy's sheer mass and structure force a re-examination of the laws of galactic formation. Normally, dark matter halos act as the invisible backbone, providing the gravitational pull necessary for gas to coalesce into stars. Gas clouds cool slowly, collapsing under their own weight, fragmenting into clusters, birthing generations of stars over cosmic timescales. The models are clear. Even in regions of high density, the assembly of a galaxy of this size would require timescales longer than the age of the universe at its observed redshift. Yet here it is, fully formed, brimming with stars, already hosting a central black hole of enormous mass, its spiral arms meticulously sculpted. Every observation is a confrontation between expectation and reality. The cinematic tension intensifies as we imagine the processes at play. We see vast clouds of hydrogen swirling like rivers of molten silver, collapsing into nascent stars and violent bursts of creation. We envision collisions with other proto-galaxies, cosmic mergers that might accelerate growth, yet even these extreme events fail to fully account for the galaxy's size. Simulations falter, unable to replicate its grandeur, leaving astronomers both frustrated and mesmerized. The laws that govern smaller, more typical galaxies seem powerless here. The universe's rules are present, but the galaxy's formation narrative has found loopholes, or perhaps it is following laws yet unknown to human eyes. Emotion enters the narrative through the scale of contradiction. Imagine standing on the edge of a precipice, looking at a structure that dwarfs all others, knowing that by all rights it should not exist. The mind struggles to reconcile the familiar with the impossible. And in this cognitive dissonance lies the tension that drives engagement. The viewer is caught between the comfort of understanding and the thrill of being utterly surprised. Scientific language transforms into storytelling, equations into narrative arcs, and data points into characters in a drama written by the universe itself. Philosophically, the galaxy becomes a symbol. It is a reminder that the cosmos is not merely a set of rules to be memorized, but a living, evolving entity, capable of surprises that challenge human arrogance. Every spiral arm, every cluster of blazing stars, every gravitational distortion serves as a reminder that the universe is vaster, stranger, and more unpredictable than our models allow. The rules we rely upon are tools, not absolute truths, and this galaxy is a cautionary tale that nature always reserves the right to exceed human expectations. As the section closes, the tension between order and anomaly is brought to its peak. We leave the audience suspended between admiration and unease, their minds alive with questions. How could a galaxy form so rapidly? What processes might have accelerated its growth beyond the known laws of physics? Could this be a one-off cosmic fluke, or does it hint at deeper, undiscovered mechanisms that govern the universe? The cinematic imagery lingers, swirling stars, immense gravitational fields, and the silent, glowing enormity of a galaxy that defies everything we thought we knew. In that lingering uncertainty, the stage is set for exploration. The rules of the cosmos have been challenged and the story is only beginning. The viewer is left with both wonder and urgency, aware that understanding this single anomaly could unlock revelations about the nature of galaxies, the limits of physics, and the hidden mechanics of a universe far stranger than we ever imagined. The impossible is not just observed, it is felt, a profound emotional resonance echoing across billions of light-years. The universe has spoken, and for the first time, it seems to laugh quietly at our assumptions, daring us to dig deeper, question harder, and imagine a cosmos where the impossible is not just possible, it exists. When we look at the night sky, we are not seeing the present. We are seeing the past. Each twinkle, each glimmer of distant light is a message sent across unfathomable distances, traveling for millions or even billions of years before it reaches our eyes. This is the strange and beautiful reality of astronomy. Telescopes are not merely instruments, they are time machines. And when we turn them toward this colossal, impossible galaxy, we are not just observing a structure in space. We are witnessing an ancient chapter of cosmic history, written long before our sun even existed. Imagine the universe as a vast, turbulent ocean in its earliest days, waves of matter and energy rippling through the dark expanse. In this primordial chaos, pockets of gas begin to collapse, igniting the first stars, scattering their light like sparks across the void. Galaxies emerge, tentative and fragile, slowly growing through collisions, accretion, and the relentless pull of gravity. Against this backdrop, the galaxy we now see seems almost like a defiant anomaly, a fully formed, gargantuan island in a sea of chaos. Its light has traveled billions of years, journeying across space-time, carrying within it the secrets of its formation. And as we capture that light, we are not merely looking. We are listening to an echo of the past, a story the universe has waited billions of years to tell. The tools we use to peer back in time are themselves marvels of human ingenuity. Telescopes like Hubble and now the James Webb Space Telescope do more than magnify, they dissect the universe across the spectrum. Infrared detectors reveal heat from nascent stars hidden in dense clouds. Spectroscopy separates light into its component wavelengths, uncovering the chemical fingerprints of elements forged in the galaxy's first generations of stars. Radio waves trace the invisible scaffolding of hydrogen gas that underpins galactic structures. Each observation is a brushstroke in a cosmic painting, revealing the shape, motion, and age of a galaxy that seems impossibly advanced for its era. As we analyze the light streaming from this gargantuan galaxy, a narrative emerges, a tale written in photons and gravitational distortions. The galaxy's spiral arms, its clusters of bright, young stars juxtaposed with ancient, red giants, tell a story of rapid, almost aggressive formation. Regions that should still be chaotic clouds of gas appear already settled into well-defined structures. Its central black hole, massive beyond expectation, hints at processes that accelerated growth far faster than any model predicts. Every photon is a messenger, a fragment of history arriving late but precise, carrying answers and new questions across the cosmic gulf. The tension in this discovery is palpable. On one hand, we are awed by the galaxy's clarity and complexity at such a distant epoch. On the other, we are unsettled by the implications. The rules of galactic evolution, so meticulously studied and simulated, cannot easily account for what we observe. Gravity, star formation rates, gas cooling. These mechanisms, though reliable elsewhere, appear insufficient to explain the galaxy's astonishing maturity. Its light is both a revelation and a provocation, forcing scientists to confront the limits of their models and the uncertainties of the early universe. The imagery is cinematic and deeply evocative. Picture the galaxy as it existed when the universe was only a fraction of its current age, a glowing beacon amid the murky backdrop of primordial darkness. Gas streams flow like rivers of liquid silver, collapsing under unseen forces into luminous clusters. The central bulge pulses with the energy of stars in rapid formation, while the spiral arms extend outward like wings carved from light itself. Dark matter halos stretch invisibly around it, a ghostly skeleton guiding the galaxy's growth, yet leaving open the possibility that something unknown accelerated its assembly. This perspective of time deepens the emotional resonance. We are not merely observers. We are travelers journeying backward across billions of years to witness events that shape the universe. The galaxy becomes more than a scientific curiosity, it is a monument to cosmic history, a living relic from an epoch long gone, frozen in light that has only just reached us. There is a humbling sense of scale here, a recognition that the universe is ancient, vast, and capable of producing wonders that dwarf our imagination. Yet with awe comes mystery. How could such a massive, structured galaxy exist at a time when the universe was so young, turbulent, and chaotic? Models predict that early galaxies should be smaller, irregular, and slowly assembling. But this galaxy is defiant, fully formed, and unerringly mature. It challenges our understanding of cosmic timelines, demanding explanations that may lie beyond conventional physics, perhaps in processes we have yet to comprehend or even imagine. As we follow the light further, we notice subtle patterns, variations in star density, chemical composition, and motion. These details hint at a violent, dynamic past, mergers with other proto-galaxies, rapid bursts of star formation, and the early growth of a black hole powerful enough to shape the galaxy's evolution. Each clue is a puzzle piece, yet no assembly of pieces fully explains the magnitude and speed of its formation. The galaxy remains a paradox, a cosmic question mark suspended in the void. The narrative tension here is not only scientific but philosophical. Peering back in time forces us to confront our own place in the universe and the fragility of our understanding. The galaxy existed billions of years before life on Earth, before human thought, before civilizations arose to wonder at the cosmos. Its light reaches us now, bridging incomprehensible distances and epochs, reminding us that the universe has always operated on scales far beyond human comprehension. The juxtaposition of human curiosity with cosmic immensity heightens the emotional stakes, blending awe, wonder, and existential reflection. By the end of this section, the audience is drawn into both the science and the story. We have journeyed across time, witnessing the galaxy in its prime, marveling at its structure and scale, and grappling with the paradoxes it presents. The light we see is ancient, yet it speaks urgently, insisting on attention, demanding questions and resisting easy answers. The galaxy is a window into the past, a testament to the universe's power to surprise, and a harbinger of mysteries yet to be unraveled. The stage is now set for deeper exploration. Having seen the galaxy as it once was, the audience is primed to investigate why its size defies expectation, how its structure came to be, and what forces, known and unknown, may have shaped this extraordinary relic of the early cosmos. The cinematic tension lingers, poised between revelation and mystery, promising that the answers we seek will challenge not only science but our very understanding of how the universe grows, evolves, and surprises us at every turn. In the vast architecture of the cosmos there are limits. Invisible boundaries set by the laws of physics dictate how stars ignite, how galaxies form, and how gravity binds the scattered chaos of matter into coherent, glowing islands. These rules have guided generations of astronomers, physicists, and cosmologists, giving them confidence that the universe, for all its grandeur, operates within understandable constraints. Yet sometimes the cosmos delivers something that seems to flout those rules entirely, a structure so colossal, so impossibly massive, that it forces us to reconsider what possible even means. This galaxy, the largest ever observed at its distance and epoch, is one such cosmic anomaly. Its existence is a direct challenge to the frameworks that underpin our understanding of the universe. The puzzle begins with scale. For a galaxy to reach this magnitude, to host hundreds of billions of stars in a single coherent structure, it must accumulate matter at rates that seem almost reckless. Gas clouds must collapse rapidly without fragmenting, dark matter halos must grow denser and more massive than our models allow, and star formation must proceed with extraordinary efficiency. Yet all evidence suggests this is exactly what happened. The galaxy is not a diffuse, chaotic collection of stars, it is a mature, structured system, with spiral arms sprawling like celestial ribbons and a central bulge hosting a black hole of extraordinary mass. Every component appears fully developed, as though time itself bent to accelerate its growth. Herein lies the tension. The universe has limits, and this galaxy appears to have ignored them. The laws of thermodynamics, gravity, and cosmic structure formation are not merely suggestions. They are constraints with observable consequences. Gas clouds can only cool so quickly, matter can only coalesce so efficiently, and energy feedback from exploding stars and active black holes usually halts or slows further growth. Yet the galaxy's rapid accumulation of mass and its structural maturity suggest that either these processes were somehow circumvented or that unknown mechanisms were at play, speeding its evolution in ways our models do not yet account for. Visualize this galaxy as a blazing metropolis rising out of the primordial darkness, its spirals like luminous highways carved through interstellar clouds, stars forming at staggering rates in clusters that glow like molten gold. The contrast between our expectations and this reality is visceral. Typical early universe galaxies are small, irregular, turbulent, a chaotic mess of nascent stars struggling to coalesce. This galaxy, however, is already a titan, a serene but overwhelming structure that feels almost arrogant in its perfection. The juxtaposition is staggering. The universe, in its infancy, produced something that seems far ahead of its time. The challenges extend beyond imagination into hard numbers. Calculations based on standard models of galaxy formation indicate that a galaxy of this mass should not exist at this stage in cosmic history. It would take far longer than the age of the universe at the observed redshift to amass such matter through mergers and accretion alone. Even the most extreme simulations of early universe conditions fail to produce galaxies of this scale with the speed observed. It is as if the galaxy flouts the cosmic speed limit, racing ahead while the rest of the universe moves at a more measured pace. The tension is not merely intellectual, it is emotional, almost narrative in quality. Imagine being a scientist staring at data that confirms something you previously thought impossible. The excitement is palpable, but it is laced with a subtle unease. Every plot, every spectral line, every measurement points to a reality that refuses to conform. The galaxy is a paradox made visible, a living question mark, demanding attention, respect, and, most of all, explanation. It challenges our assumptions not only about galactic growth but about the underlying principles that govern matter on the grandest scales. This defiance extends to the galaxy's internal processes. Star formation rates are unusually high, suggesting that gas is collapsing into new stars at unprecedented speeds. Meanwhile, feedback from supernovae and the central black hole, which normally regulate growth, seems insufficient to halt or slow the process. Its mass distribution is unusually coherent, implying that dark matter halos may be denser or differently structured than previously thought. Every feature, every metric, is a contradiction, a tension between what physics predicts and what the cosmos has delivered. The narrative becomes cinematic in the way it balances tension and revelation. We drift past the galaxy's spiral arms, tracing the flow of star-forming regions, feeling both awe and unease. The beauty of its structure is undeniable, yet each luminous filament serves as a reminder of the anomaly's impossibility. The galaxy is both familiar and alien, a reflection of patterns we recognize, scaled to dimensions we cannot fully comprehend. In this interplay of recognition and estrangement lies the emotional core of the discovery. The viewer is awed by what they see, yet unsettled by what it implies. Philosophically, the galaxy confronts us with questions that transcend astrophysics. If such a massive structure can form so quickly, what does it say about the flexibility of cosmic law? Are there processes operating in the universe that we have yet to understand, mechanisms that accelerate growth, reshape matter, or bend time in subtle ways? The galaxy becomes a symbol of the unknown, a monument to the universe's ability to surprise, and a challenge to the arrogance of human certainty. As this section progresses, the tension is further amplified by the contrast between the galaxy and its surroundings. Nearby galaxies, forming more slowly and irregularly, highlight just how extraordinary this titan truly is. While the cosmic landscape is dotted with fledgling systems struggling to coalesce, this galaxy towers above them, a fully formed empire in a universe still finding its footing. The visual and conceptual contrast underscores the improbability of its existence, driving the narrative forward with suspense and emotional resonance. By the end of this exploration, the audience is left in a state of heightened curiosity and awe. We have seen a galaxy that challenges every assumption about size, growth, and possibility in the early universe. Its very presence forces us to question the rules we thought were immutable, to confront the limits of our understanding, and to consider that the universe may operate on scales and principles far stranger than we have imagined. The galaxy does not simply exist. It provokes, it inspires, and it unsettles, leaving a lingering sense that in the grand story of the cosmos, we have only begun to turn the pages. This impossible giant, radiant and defiant, becomes a gateway into deeper mysteries. Its size should not be possible, yet here it is, a living testament to the universe's capacity for wonder, complexity, and defiance. And as we prepare to map it, analyze it, and attempt to explain it, one question remains above all others. If something this massive can form so quickly, what other secrets lie hidden in the depths of the cosmos, waiting to rewrite everything we think we know? To understand the enormity of this galaxy, one must first see it in its full scope, not as a faint speck of light on a screen, but as a sprawling, multi-layered structure with complexity that rivals entire clusters of ordinary galaxies. Mapping it is not a simple task. It is a painstaking, almost reverential process, one that combines observations from multiple telescopes, wavelengths, and instruments. Each slice of data reveals a new layer of its anatomy: the glowing arms where stars are born in turbulent nurseries, the dense central bulge containing a black hole of unimaginable mass, and the extended halo of dark matter that cradles the galaxy in a ghostly embrace. In essence, to map this titan is to peel back the layers of a cosmic enigma, revealing the intricate machinery of an object that seems almost alive in its sheer scale and orchestration. The first step in this mapping journey is to visualize the galaxy's luminous structure. Its spiral arms sweep outward in grand, elegant curves, dotted with clusters of brilliant blue stars, fiery nebulae, and pockets of dense molecular gas. These arms, stretching across hundreds of thousands of light-years, are rivers of light and matter, each filament pulsating with the energy of star formation. The contrast between these luminous highways and the dark spaces in between creates a sense of depth and movement, as if the galaxy itself were breathing, alive with energy and motion. Each star, each cloud of gas, is a marker on the map of a universe-defying entity, yet the whole remains coherent, majestic, and astonishingly symmetrical. Beyond the visible structure lies the unseen backbone, the dark matter halo. Unlike the glittering arms, this component cannot be seen directly. Its presence is inferred from gravitational effects, the way stars orbit the galactic center, and the bending of light from more distant objects behind it. In this galaxy, the halo appears unusually massive and extended, providing a scaffold that supports the galaxy's extraordinary size. Imagine a vast, invisible web, holding the galaxy together while shaping the paths of stars and gas clouds. Without this hidden skeleton, the luminous beauty we see would collapse into chaos, Yet even with it, the formation and scale of the galaxy remain perplexing, pushing the limits of current cosmological models. The central bulge is another focal point in the mapping process. Here, the galaxy's supermassive black hole dominates, a gravitational titan whose mass rivals or exceeds anything previously observed in similar early universe galaxies. Surrounding it is a dense concentration of stars, tightly packed and orbiting at extraordinary speeds. The energy radiating from this region, whether in the form of high-energy X-rays, infrared emissions, or relativistic jets, is both mesmerizing and intimidating. It is a reminder that even in the midst of breathtaking beauty, the galaxy harbors forces of unimaginable power, capable of shaping the formation of stars, sculpting gas clouds, and influencing the growth of the entire system. Mapping also reveals the galaxy's chaotic yet harmonious zones of star formation. Some regions are violent and turbulent, with clouds of gas colliding at high velocities, igniting bursts of new stars and brilliant explosions of light. Others are calmer, serene swathes of space where stars emerge gradually, like sparks slowly kindling a distant fire. The diversity of these regions speaks to a complex internal ecosystem, one that has managed to balance creation and destruction with an efficiency that seems almost unnatural. The galaxy's ability to sustain such high rates of star formation while maintaining structural integrity is a key part of the mystery that makes it both fascinating and defiant of expectation. Spectroscopy adds another layer of understanding, revealing chemical composition and motion. By analyzing the light from individual stars and gas clouds, scientists can map where elements like hydrogen, helium, oxygen, and heavier metals are concentrated. These chemical fingerprints tell a story of rapid evolution. Stars forming, aging, exploding, and seeding their surroundings with new elements, all on a timeline that challenges conventional understanding. The distribution of metals, the temperature of gas clouds, and the motion of stars collectively paint a picture of a galaxy that matured at an astonishing pace, defying the slow, measured growth observed in most early universe galaxies. As the map comes together, the contrast between this galaxy and typical galaxies of its era becomes even more striking. Nearby galaxies, often small, irregular, and chaotic, highlight the anomaly's coherence and scale. Where others are struggling to assemble stars into organized structures, this galaxy sprawls majestically, almost arrogantly, across the cosmic landscape. Its size alone makes it a standout, but the mapping process reveals something deeper. The galaxy is not merely large, it is complete, mature, and extraordinarily ordered for its age. Every arm, every cluster, every dense core tells a story of accelerated formation and hidden forces shaping its destiny. The cinematic potential of mapping this titan is immense. Imagine sweeping shots that glide along spiral arms, passing luminous star clusters, diving into turbulent clouds of gas, and then pulling back to reveal the central black hole's awe-inspiring dominance. Visualizations shift between the visible and invisible, between light and dark matter, creating a dynamic, layered portrait of a galaxy that is both beautiful and impossible. This is not just data, it is storytelling, translating numbers and spectra into imagery that evokes wonder, tension, and profound curiosity. Mapping also uncovers subtle anomalies that hint at even deeper mysteries. Some regions rotate faster than expected, others contain unusually dense clusters, and certain filaments of gas appear to defy standard gravitational models. Each discrepancy is a narrative beat, a clue that pushes scientists to question whether unknown processes, exotic physics, or accelerated formation mechanisms might be at play. The galaxy is not a static object. It is a living puzzle, its structure a guidebook to questions humanity has yet to answer. By the end of this section, the audience gains a holistic view of the galaxy's anatomy and its extraordinary scale. The mapping process transforms abstract data into a tangible, awe-inspiring structure that the mind can visualize and the imagination can roam. Every layer, from luminous arms to dark matter halo, from the central black hole to star-forming nurseries, reveals a galaxy that is as complex as it is massive, as ordered as it is anomalous. The enormity and intricacy of the structure leave viewers suspended between admiration and disbelief, setting the stage for the next phase of exploration, understanding the forces at the heart of this cosmic titan, and unraveling the mysteries that allowed it to form against the odds. In essence, mapping the titan is more than science, it is storytelling on a cosmic scale. Each observation, each plotted curve, each spectral line is a sentence in a grand narrative of formation, growth, and cosmic defiance. And as we trace its structure, we begin to see not only a galaxy but a testament to the universe's ability to surprise, challenge, and inspire awe, leaving humanity with both wonder and a profound sense of our own smallness in the face of its magnitude. At the heart of every galaxy lies a secret, a singularity around which billions of stars dance in silent, invisible harmony. In most galaxies, this central black hole is already a force to be reckoned with, a gravitational engine whose mass can rival billions of suns. But in this colossal galaxy, the central black hole is something beyond comprehension. A leviathan, a monster whose gravity dominates everything around it, shaping the galaxy's structure, its star formation, and its destiny. Its presence is not just a fact of physics. It is a focal point of mystery, awe, and even fear, a reminder that at the core of beauty and light there often lies a force of darkness and unimaginable power. As we approach this region, the imagery becomes cinematic and almost tactile. Stars whirl around the central bulge at dizzying speeds, tracing elliptical orbits dictated by the black hole's immense pull. Gas clouds spiral inward in luminous streams, colliding, heating, and igniting bursts of radiation as they are stretched and compressed by tidal forces. Dust glows in the infrared, revealing structures invisible to optical telescopes, while jets of particles erupt from the poles, shooting energy into the galaxy like lances of light. The monster is not dormant, it is a dynamic, restless entity, a gravitational heart whose activity echoes across hundreds of thousands of light-years. The enormity of the black hole is staggering. Estimates suggest it could be tens of billions of solar masses, rivaling or even exceeding the largest black holes known in the nearby universe. For comparison, the black hole at the center of our Milky Way is only about 4 million times the mass of the Sun. This means that the central engine of this galaxy is not just massive, it is extraordinary in every sense, a gravitational anchor whose influence stretches far beyond the luminous stars visible to our instruments. The very existence of such a black hole in the early universe raises profound questions about cosmic evolution. How did it grow so quickly, and what role did it play in shaping the galaxy around it? The monster at the center is also a key player in the galaxy's paradoxical maturity. In most galaxies, black holes grow slowly, accumulating mass over eons, feeding on gas and stars that drift too close to the event horizon. Their growth is intertwined with the evolution of the surrounding galaxy, regulating star formation through feedback mechanisms that can heat or expel gas. But in this galaxy, the black hole appears to have accelerated its growth at an extraordinary rate. Its influence is seen in the coherent spiral arms, the organized clusters of stars, and the regulation of gas clouds, suggesting that this central monster may have orchestrated much of the galaxy's rapid development. The paradox is profound. While black holes are often destructive, this one seems to have played a creative, even stabilizing role, shaping a galaxy that should not exist by any conventional standard. Approaching the event horizon in imagination, the scale and danger become almost palpable. Time dilates, light bends, and physics itself seems to stretch to its limits. Any matter that crosses the threshold is forever lost, drawn into a singularity where density and gravity become infinite. Yet, paradoxically, this destructive center enables the galaxy's grandeur. The black hole is both a predator and a protector, a chaotic core that fosters order on cosmic scales. Observing it challenges not only our understanding of gravity but also our perception of creation and destruction in the universe. High-energy emissions from the region paint a picture of violent activity. X-rays flare as matter is ripped apart and heated to millions of degrees. Relativistic jets pierce through the surrounding space, shaping the galaxy's halo and influencing star formation across vast distances. The interplay of attraction and radiation creates a delicate balance. Too much activity and the galaxy would be stripped of gas and star formation would cease. Too little and the central region might collapse into disorder. This fine-tuned tension underscores the black hole's role as both architect and destroyer, a force that shapes reality through extremes of gravity and energy. Spectroscopic analysis further deepens the mystery. By observing the motion of stars and gas near the core, scientists can infer the black hole's mass and influence. The velocities are astonishing, indicating a concentration of mass that conventional models cannot easily explain given the galaxy's age. The presence of such a massive black hole so early in cosmic history suggests accelerated processes, perhaps involving direct collapse mechanisms or rapid mergers of smaller black holes. Each measurement is a story in itself, a clue to a puzzle that challenges the very timeline of cosmic evolution. The emotional impact of contemplating the central black hole is profound. It evokes a mixture of fear, reverence, and awe. Here lies a force that could destroy entire star clusters, yet it also enables the galaxy's existence. It is the ultimate expression of cosmic power, a reminder that the universe contains entities that dwarf human comprehension, entities whose scale and influence stretch across light years and eons. In narrative terms, the black hole serves as a character in its own right. A monster, a king, a hidden hand shaping the story of an impossible galaxy. Philosophically, the black hole invites reflection on the nature of extremes. It embodies contradictions, creation and destruction, order and chaos, visible light and invisible gravity. Its presence in such a young galaxy forces us to reconsider assumptions about how quickly structures can evolve in the universe, how mass accumulates, and how energy interacts with matter on the largest scales. The monster at the center is not merely a gravitational phenomenon, it is a catalyst for questioning everything we thought we knew about the cosmos. By the end of this exploration, the audience is left with both awe and tension. The central black hole is a reminder that the universe operates on scales and with forces that are almost unimaginable. It dominates the galaxy, shapes its evolution, and yet remains an enigma, a singularity that cannot be fully understood or visualized. Its role is both destructive and creative, a force that has helped build the galaxy while simultaneously threatening to undo it. In this way, the central black hole becomes more than an object of study, it is a narrative anchor. Its presence reinforces the stakes of the galaxy's anomaly, emphasizing the tension between known physics and cosmic possibility. It is a monster not in the sense of terror alone, but in scale, influence, and mystery, a focal point that draws both scientists and viewers into the heart of the galaxy's impossible story. The exploration of this monster at the center sets the stage for the next chapters. Understanding how the galaxy produces stars at such incredible rates, how its chemical composition hints at a strange past, and how the interplay between gravity, matter, and energy continues to defy expectation. The monster is not merely at the center. It is at the heart of the mystery, an essential piece of a cosmic puzzle that will continue to captivate and challenge us for years to come. Across the sprawling arms of this colossal galaxy, the universe performs a spectacle of creation unlike anything we have seen before. Entire regions blaze with the birth of stars, each one igniting with furious intensity, forming what astronomers call stellar nurseries. Yet in this galaxy, these nurseries are on an unprecedented scale, vast, turbulent, and glowing with an almost blinding brilliance. The rate of star formation defies conventional models, with hundreds or even thousands of stars igniting in regions where, under normal cosmic conditions, only a handful would appear. It is as if the galaxy is a factory running beyond capacity, churning out stars in a relentless, almost obsessive drive toward luminosity and mass. Imagine flying through one of these regions. Swirling clouds of gas, thick and luminous, collapse under gravity's relentless pull. Massive stars ignite in brilliant bursts, casting their searing light into surrounding nebulae, which glow in vibrant blues and reds. The energy is so intense that radiation pressure pushes against nearby gas clouds, sculpting filaments, pillars, and cavities in an intricate cosmic ballet. Collisions between clouds are frequent and violent, producing shocks that further trigger star formation in a chain reaction. The pace of creation is staggering. In what feels like an instant on cosmic timescales, new clusters of stars flare into existence, adding to the galaxy's already unimaginable mass. The scale of these star-forming regions is itself astonishing. Where in the Milky Way a giant molecular cloud might produce a few thousand stars over millions of years, in this galaxy, entire clusters form at rates hundreds of times faster. Some regions span tens of thousands of light-years, glowing with the collective brilliance of millions of newly formed stars. The sheer density and speed of star formation suggest an environment optimized for rapid growth, a galaxy that seems determined to reach extraordinary proportions in record time. Every new generation of stars adds to the galaxy's gravitational heft, further accelerating the assembly of its structure. But such extreme star formation is not without consequence. The energy output from massive stars is immense, and their lifespans, though short, end in spectacular supernova explosions. These cataclysms inject enormous energy into surrounding gas, generating shockwaves that can either trigger further star formation or disrupt nearby clouds, halting the process. In this galaxy, however, the balance appears finely tuned. Despite the violence, star formation continues unabated, suggesting that either the galaxy's gravity is unusually strong, anchoring the gas, or that some yet undiscovered mechanism stabilizes the environment. The result is a paradox. Chaos produces order, destruction feeds creation, and the galaxy continues to grow larger and more luminous with each passing million years. The distribution of these star-forming regions adds to the spectacle. The spiral arms are ablaze with clusters of young hot stars, while the central bulge hosts older, more evolved populations. The arms act like conveyor belts, channeling gas into regions where it can collapse and ignite, while also feeding the central black hole, which in turn influences further star formation through feedback processes. This interwoven system of creation, regulation, and growth is a testament to the galaxy's extraordinary complexity and hints at a level of orchestration that challenges our understanding of early universe dynamics. Observationally, these regions reveal themselves in brilliant detail. Infrared imaging penetrates dense clouds of dust, unveiling hidden pockets of star formation that optical telescopes cannot see. Radio observations trace the distribution of hydrogen gas, the raw material for new stars, while ultraviolet light highlights the youngest, hottest stars blazing in energetic blue. Spectroscopy provides a chemical map, showing regions enriched with heavier elements from previous generations of supernovae, indicating a surprisingly rapid chemical evolution. All these data points converge to tell a story of a galaxy operating at maximum efficiency, producing stars at a rate far beyond expectations for its age and size. The cinematic effect of visualizing these star factories is profound. Imagine sweeping across a galaxy whose arms glow like rivers of molten light, each cluster of stars a spark in a vast forge of creation. Pillars of gas tower like cathedral spires, illuminated by the newborn stars within. Supernovae explode in silent fury, scattering elements that will seed future generations. The entire galaxy pulses with energy, a living, breathing organism whose heartbeat is measured in bursts of stellar ignition. The contrast between the serenity of the galaxy's grand spiral structure and the violent, energetic chaos within its arms creates a tension that is both beautiful and unsettling. This extreme rate of star formation also raises fundamental questions about cosmic history. How could a galaxy achieve such efficiency so early in the universe? What mechanisms allowed gas clouds to collapse so quickly without fragmenting into smaller, less productive regions? How did the interplay between gravity, feedback, and dark matter conspire to sustain such a rapid pace of creation? Each question hints at unknown processes or conditions in the early universe, suggesting that our current models may be incomplete or missing critical physics that operate under extreme conditions. Emotionally, the spectacle of these star factories evokes awe and wonder. There is a primal thrill in witnessing creation on such a scale, in seeing the universe transform gas into light with such speed and intensity. Yet there is also a sense of unease, a recognition that these processes are extraordinary, defying expectations, and hinting at cosmic forces we barely understand. The galaxy's vitality, its relentless drive to produce stars, underscores both the power and mystery of the universe. By the end of this section, the audience is fully immersed in the galaxy's inner workings. The arms, the clusters, the explosive energy of creation, and the delicate balance between chaos and order paint a picture of a galaxy operating at the extreme limits of possibility. Its star formation is not just an astronomical process, it is a narrative of energy, growth, and cosmic ambition, a story of a galaxy that refuses to conform to the timelines and rules that govern its peers. These extreme star factories set the stage for the next chapters of discovery. They connect directly to the galaxy's chemical composition, the dynamics of its central black hole, and the paradoxical rapidity of its growth. In witnessing this furious creation, viewers understand not just the scale, but the vitality and audacity of the galaxy, an entity that challenges everything we thought we knew about how stars and indeed galaxies form in the universe. This is a galaxy alive with energy, ambition, and mystery, a living laboratory where the limits of cosmic possibility are tested and exceeded at every turn. Every star carries a story, and every galaxy is a living archive of the universe's history. In this colossal, anomalous galaxy, the chemical composition of its stars and gas clouds is not merely data, it is a narrative written in the language of atoms, a record of violent births, explosive deaths, and cosmic alchemy stretching back billions of years. By studying these chemical fingerprints, astronomers can reconstruct the galaxy's mysterious past, tracing the processes that allowed it to grow so rapidly and become so massive when the universe itself was still young and chaotic. The story that emerges is both wondrous and unsettling, filled with contradictions that deepen the enigma at the heart of this cosmic giant. The journey begins with spectroscopy, the practice of splitting light into its component colors to reveal the presence of specific elements. Each wavelength, each absorption or emission line, tells us something about the age, composition, and history of stars and gas clouds. In this galaxy, the spectra reveal a surprising richness of elements: oxygen, carbon, iron, and other metals, that suggest rapid chemical evolution. Stars have already lived and died, seeding the interstellar medium with heavy elements far earlier than expected. For comparison, most early universe galaxies of similar age display much lower metallicity, indicating that the buildup of heavy elements is typically a slow, gradual process. Yet here, the galaxy has accelerated chemical enrichment to an extraordinary degree. The implications are profound. The presence of mature chemical signatures suggests that multiple generations of stars formed, evolved, and exploded in supernovae within a relatively short time span. This raises questions about the conditions that allowed such rapid cycles of stellar birth and death. Gas clouds, typically fragile and easily disrupted by feedback from supernovae or radiation pressure, appear to have survived repeated violent events, continuing to collapse into new stars. It is as though the galaxy's environment was uniquely conducive to sustained star formation, a factory not only producing stars but doing so with an efficiency that defies conventional astrophysical models. Cinematic imagery emerges naturally from these observations. Picture clouds of glowing gas, suffused with elements forged in the cores of dying stars, illuminated by the light of newborn stellar clusters. Supernovae detonate like fireworks, scattering enriched material across vast distances, while streams of gas swirl in graceful arcs toward the galaxy's center. Each explosion, each spark of light, is a chemical echo of the past, a marker of the violent processes that shaped the galaxy's evolution. The combination of beauty and destruction is mesmerizing, creating a narrative tension that mirrors the scientific mystery. The galaxy is simultaneously orderly and chaotic, youthful and ancient, growing faster than it should, and yet following its own hidden logic. Further analysis of the chemical composition reveals regional variations that deepen the intrigue. The central bulge contains stars with higher metallicity, indicating intense early star formation and rapid enrichment, likely influenced by the supermassive black hole at the galaxy's core. In contrast, some outer regions show slightly lower metal content, suggesting infall of pristine gas from the cosmic web or minor mergers with smaller proto-galaxies. This patchwork of chemical signatures hints at a dynamic and complex evolutionary history, one in which growth, accretion, and internal processes interplay to create the galaxy's extraordinary scale. These chemical traces also provide indirect evidence of past cosmic violence. Supernova remnants, mapped through spectral analysis, suggest that clusters of massive stars lived fast and died young, shaping the surrounding environment in both constructive and destructive ways. The feedback from these explosions would normally regulate further star formation, heating gas, and dispersing clouds. Yet in this galaxy, the effect seems moderated or counterbalanced, allowing stellar nurseries to persist at unprecedented rates. It is a paradox that challenges both theory and imagination, creation thriving amid destruction, growth proceeding amid chaos, and the chemical record itself whispering of forces not fully understood. The story becomes even more compelling when considering the galaxy's age. At a stage in the universe's history when most galaxies are irregular, small, and chemically primitive, this galaxy already exhibits mature chemical signatures. Its stars contain heavier elements in ratios that suggest multiple generations of enrichment, a rapid acceleration of processes that normally require billions of years. The chemical evidence aligns with structural and dynamical anomalies, reinforcing the notion that this galaxy is an outlier, a cosmic anomaly that refuses to conform to established models. Emotionally, the chemical narrative evokes awe and mystery. Each element, each ratio of metals, is a relic of processes long gone, a message in a bottle sent across billions of years. Observing them is like peering into the fossilized memory of a galaxy, understanding its life story in the language of physics and chemistry. Yet the story is incomplete. While the chemical clues reveal rapid enrichment and accelerated evolution, they also highlight contradictions, regions where models fail, processes that remain unexplained, and timelines that defy expectation. The galaxy becomes both familiar and alien, a cosmic paradox wrapped in glowing clouds of elemental evidence. Philosophically, these chemical echoes provoke reflection on the nature of time, causality, and cosmic creativity. They suggest that the universe is capable of constructing massive, complex systems far faster than we anticipate, leveraging unknown mechanisms or environmental conditions to accelerate evolution. The galaxy is a laboratory of extremes, demonstrating that even in the early universe, nature could produce structures of breathtaking scale, efficiency, and intricacy. Each atomic fingerprint is a testament to the forces at work, both visible and hidden, shaping matter on colossal scales. By the end of this section, The audience appreciates the galaxy not merely as a collection of stars and gas but as a chronicle of cosmic history, encoded in its chemical composition. The enriched elements, the variation across regions, and the rapid evolution they imply all serve to heighten the mystery, illustrating how a galaxy so massive could assemble so quickly in a universe that was, by most measures, still in its adolescence. The chemical echoes are more than data. They are storytelling elements, narrating a saga of creation, destruction, and rapid evolution that challenges our understanding of cosmic timelines. In this way, chemistry becomes a window into the galaxy's soul, revealing not just what it is but how it came to be. Each molecule, each element, is a clue in a puzzle that spans billions of years, connecting the galaxy's structure, its star-forming regions, and its central black hole. The past is written in fire and radiation, in explosive deaths and luminous births, yet the story remains incomplete, urging the audience and humanity itself to seek deeper, to explore further, and to confront the profound mysteries of a universe capable of producing something both beautiful and impossibly advanced. Time, in the cosmos, is measured not in minutes or hours, but in millions and billions of years. Galaxies grow slowly, merging with neighbors, forming stars in measured cycles, and accumulating mass at a pace dictated by the laws of physics. Each stage of their evolution is constrained by the universe's age, the availability of gas, and the influence of gravity and dark matter. Yet this galaxy defies all such temporal expectations. It exists fully formed, sprawling, and mature at a time when, according to our most reliable models, it should barely be beginning its journey. The paradox is not subtle. It is stark, almost audacious in its challenge to conventional cosmology. The first shock comes from redshift measurements which tell us how far away, and therefore how long ago, we are observing this galaxy. At such distances, the universe was a fraction of its current age, a tumultuous arena where most galaxies were small, irregular, and chemically primitive. Stars were young, gas clouds chaotic, and the cosmic web itself still in formation. Yet this galaxy appears fully mature, a massive spiral with coherent structure, dense star clusters, and a central black hole of extraordinary mass. Its size and complexity suggest processes operating at speeds that stretch our understanding of cosmic physics. It is a living contradiction, a monument to the possibility that the early universe could produce giants far earlier than we imagined. The implications of this temporal anomaly ripple through astrophysics. Standard models of galaxy formation rely on gradual growth. Dark matter halos accumulate slowly, gas collapses over millions of years, and stars form in sequential generations. Feedback from supernovae and black hole activity regulates growth, ensuring that galaxies evolve over predictable timescales. But in this galaxy, the timeline appears compressed. Star formation occurred at a furious pace, chemical enrichment advanced rapidly, and the central black hole grew to colossal proportions, all within a cosmic epoch previously thought insufficient for such development. It is as if the universe pressed fast forward, creating a titan in a fraction of the expected time. Visualizing this acceleration is cinematic in its impact. Imagine a spiral galaxy unfolding like a vast cosmic ribbon, star clusters igniting simultaneously in bursts of brilliant light, gas streams converging rapidly toward the center, and supernovae detonating in cascading waves. The galaxy pulsates with energy, each flash of light a heartbeat in a system that has grown far ahead of its peers. Around it, smaller, irregular galaxies struggle to assemble, highlighting the stark contrast between ordinary cosmic timelines and the extraordinary pace of this anomaly. The viewer feels both awe and unease, recognizing the scale and speed while questioning the mechanisms that made it possible. The compression of time also has profound implications for the galaxy's internal dynamics. Rapid star formation produces enormous radiation and feedback, which typically disrupts gas clouds and halts further growth. Yet here, the galaxy appears to have managed a delicate balance, sustaining high star formation rates without self-destructing. Its central black hole, already massive, likely played a stabilizing role, regulating inflows and outflows of gas to maintain structure and fuel ongoing stellar creation. Every aspect of the galaxy's evolution is accelerated yet orchestrated, a masterclass in cosmic efficiency that challenges every assumption about how galaxies mature. This defiance of timelines also raises questions about the early universe itself. Were the conditions in certain regions uniquely conducive to rapid growth? Did this galaxy form in a dense cosmic environment, with abundant gas streams feeding its expansion? Or are we witnessing the effects of unknown processes, perhaps exotic physics, that allow matter to collapse and coalesce faster than conventional models predict? Each possibility stretches our imagination and underscores the limits of human understanding, revealing that the universe may operate on scales, speeds, and mechanisms far beyond what we currently comprehend. The narrative tension is heightened by contrast. Surrounding galaxies remain small, irregular, and turbulent, adhering to the conventional cosmic timeline. They grow, they merge, they slowly enrich chemically. Against this backdrop, the anomaly stands out as a defiant giant, a beacon of accelerated evolution, forcing observers to confront the gulf between expectation and reality. The visual and conceptual juxtaposition is striking. Ordinary galaxies labor under the weight of time, while this titan seems almost to have leaped ahead, fully formed and unapologetically massive. From an observational perspective, multiple techniques confirm the timeline anomaly. Infrared and optical imaging reveal mature spiral arms and dense stellar populations. Spectroscopic analysis shows advanced chemical enrichment, implying multiple generations of star formation. Measurements of gas dynamics indicate the presence of an unusually massive central black hole. Each independent line of evidence converges to reinforce the conclusion: the galaxy is far more evolved than its age should allow, defying cosmic timelines with a clarity that leaves little room for doubt. Emotionally, this compression of time evokes a mixture of wonder and existential reflection. We are confronted with a system that matured billions of years before the Milky Way even existed, a structure that existed when the universe was still in its infancy. The enormity of its rapid development challenges our perception of time itself, making us reconsider not only how galaxies evolve but how the universe orchestrates the dance of matter and energy on grand scales. It is awe-inspiring to witness, but also disorienting. A reminder that cosmic time flows differently than human intuition suggests. Philosophically, the galaxy's accelerated timeline raises profound questions about possibility, probability, and the hidden potential of the universe. If such rapid growth is achievable, what else might the cosmos be capable of? Are there other anomalies waiting to be discovered, challenging the constraints we have assumed to be universal? The galaxy becomes a symbol of cosmic audacity, a reminder that the universe is capable of creating extraordinary structures in defiance of expectation, and that our models, however sophisticated, may always be incomplete. By the end of this section, the audience fully appreciates the temporal paradox posed by this galaxy. It is not simply large or luminous, it is ahead of its time, a defiant monument to accelerated evolution. The narrative tension between conventional expectations and observed reality is at its peak, leaving viewers to grapple with both scientific intrigue and emotional awe. The galaxy's defiance of cosmic timelines sets the stage for deeper inquiry, understanding the forces that allowed such rapid growth, examining the interplay between star formation and black hole evolution, and confronting the possibility that the universe operates on principles far stranger than previously imagined. In essence, this section transforms the concept of cosmic time from an abstract measurement into a tangible narrative element. The galaxy is not just observed, it is experienced across time, revealing both the speed and scale of its evolution in ways that captivate the imagination and challenge the intellect. It is a system that refuses to conform, a cosmic anomaly whose rapid maturation underscores the mysteries still hidden in the early universe, and a reminder that in the story of creation, time itself can be as flexible, astonishing, and unpredictable as the structures it governs. Beneath the brilliance of stars and the luminous glow of gas clouds lies a hidden force, invisible yet omnipresent, shaping the universe on scales both vast and subtle. This force is dark matter, an elusive, enigmatic substance that neither emits nor absorbs light, yet exerts a gravitational pull that governs the formation of galaxies, the motion of clusters, and the cosmic web itself. In this colossal galaxy, dark matter is not just a background player. It is the invisible architect that allows an object of such unprecedented size and complexity to exist. Its role is profound, mysterious, and essential to understanding how the universe can defy expectations with structures that challenge everything we thought we knew. The concept of dark matter is itself a story of cosmic detective work. Scientists inferred its existence through gravitational effects that could not be explained by visible matter alone. Galaxies rotate faster than the mass of their stars and gas would allow, clusters of galaxies move in ways that defy visible mass, and the large-scale structure of the universe, the cosmic web of filaments and voids, suggests an invisible scaffold holding everything together. Dark matter acts as this scaffold, providing the gravitational framework on which galaxies assemble. In the case of this enormous galaxy, the dark matter halo is not just supportive, it is extraordinary in both mass and reach, enabling a system that should not exist under ordinary conditions. Mapping this invisible architect is a challenge of ingenuity. By observing the motion of stars and gas, astronomers can infer the distribution of dark matter. In this galaxy, stars in the outer regions orbit the center at unexpectedly high velocities, indicating that a massive halo extends far beyond the luminous arms. Gravitational lensing, where the galaxy bends the light of more distant objects behind it, further reveals the hidden mass, confirming that the dark matter halo is both enormous and dense. This halo provides the gravitational glue that holds the galaxy together, anchoring its sprawling spiral arms and stabilizing regions of rapid star formation that would otherwise disperse. The presence of such a massive dark matter halo has profound implications. It suggests that the early universe could assemble large structures more quickly than models predict, provided sufficient dark matter density. The halo channels gas into the galaxy, fuels star formation, and stabilizes the dynamics of the system. Without it, the galaxy might never have achieved coherence, collapsing into chaotic fragments rather than forming the majestic spiral we observe. In this sense, dark matter is not passive. It is an active, shaping force, silently orchestrating the growth of an impossible cosmic giant. Visualizing dark matter is an exercise in imagination. Picture an invisible web stretching across hundreds of thousands of light years, its strands bending and pulling, guiding clouds of gas and stars into place. Within this web, the luminous galaxy unfolds, its spiral arms tracing the underlying gravitational currents, its star-forming regions nestled along invisible filaments. The galaxy appears to float upon an unseen ocean of mass, a brilliant island in a dark, silent sea. The contrast between the visible beauty of stars and the unseen architecture of dark matter amplifies the mystery and cinematic tension, reminding viewers that much of the universe's story is hidden from plain sight. Dark matter also interacts indirectly with the galaxy's central black hole and star formation. Its gravitational pull helps funnel gas toward the core, feeding the supermassive black hole and enabling the rapid growth observed in the early universe. At the same time, it stabilizes the spiral arms, allowing star factories to operate at extreme efficiency without being disrupted by turbulence or supernova feedback. In this galaxy, dark matter is both a foundation and a facilitator, a silent partner in the creation of a system that seems to bend the rules of cosmic evolution. The chemical composition of stars and gas also hints at dark matter's influence. Regions of rapid star formation, accelerated chemical enrichment, and dense stellar clustering are all supported by the halo's gravitational field. It is as if the invisible framework not only holds the galaxy together but sets the pace for its evolution, dictating where gas flows, where stars ignite, and where chemical enrichment proceeds most efficiently. The interplay between visible and invisible matter creates a complex, multi-layered narrative of growth and orchestration. Emotionally and philosophically, dark matter adds depth to the story of this galaxy. It is a reminder that the universe operates on levels that elude human perception, forces that shape reality without ever being seen. The galaxy's brilliance, size, and complexity are possible only because of an unseen influence, a force that challenges our intuition and underscores the limits of observation. Dark matter becomes both a mystery and a revelation. It is the hidden hand guiding cosmic history, the scaffolding of possibility, and a symbol of the unknown forces that make the universe capable of extraordinary phenomena. The cinematic potential of dark matter is immense. Imagine sweeping visualizations of the galaxy overlaid with ghostly filaments, tracing the paths of gravitational influence, showing how stars and gas follow invisible contours. As the camera glides through spiral arms, we see not just the luminous stars but the currents of unseen mass that give them structure, a dance choreographed by a force we cannot see yet whose presence is undeniable. The tension between the visible and invisible, between beauty and mystery, elevates the narrative, making the galaxy both comprehensible and profoundly alien. By the end of this section, the audience recognizes that the galaxy's impossibility is not only a product of luminous matter but of the dark, invisible forces underpinning it. The enormous size, rapid growth, and structural coherence of the galaxy are all made possible by dark matter, an unseen architect whose influence shapes every star, spiral arm, and chemical signature. Understanding this component is essential to grasping the galaxy's story, and it also opens broader questions about the nature of the universe. How much do we truly understand about the forces shaping cosmic evolution, and how many other hidden architects may be guiding the formation of structures yet to be discovered? In essence, dark matter is the silent protagonist in the saga of this galaxy. Its invisible presence explains the impossible, stabilizes the chaotic, and enables the extraordinary. Without it, the galaxy could not exist as we see it. With it, the universe demonstrates both elegance and audacity, revealing a cosmos far stranger, more intricate and more beautifully orchestrated than imagination alone could conceive. Galaxies are not solitary wanderers drifting aimlessly through the void. They are social entities interacting, colliding, and merging in a grand cosmic dance that has shaped the universe for billions of years. These interactions are both destructive and creative, tearing apart stars and gas clouds while simultaneously triggering waves of star formation, redistributing matter and accelerating growth. In the case of this colossal galaxy, evidence suggests that its extraordinary size and maturity may not be the result of solitary evolution alone, but of a history punctuated by galactic collisions, violent yet transformative encounters that helped forge a structure far larger and more complex than typical early universe galaxies. Imagine the scene billions of years ago, two or more nascent galaxies, turbulent and chaotic, approaching each other under the inexorable pull of gravity. Gas clouds collide, stars are thrown into new orbits, and tidal forces stretch and warp the galaxy's shapes into long luminous tails. These collisions are not instantaneous. They unfold over millions of years, each encounter reshaping the distribution of matter and igniting bursts of star formation. In this galaxy, the remnants of such interactions may still be visible in faint stellar streams, asymmetries in the spiral arms, and pockets of unusually dense star clusters. Each feature is a fossil of past encounters, a chemical and structural echo of a history defined by violence and creation. Galactic collisions play a crucial role in accelerating growth. When galaxies merge, their dark matter halos combine, deepening the gravitational well and allowing more gas to collapse into new stars. Gas clouds that would otherwise drift slowly are funneled toward the center, fueling the growth of the central black hole and igniting intense bursts of star formation. In this way, collisions act as cosmic accelerators, compressing timescales and enabling galaxies to achieve sizes and masses far beyond what isolated evolution would permit. The magnitude of this galaxy suggests that it may have undergone multiple such events, each one contributing to its defiance of conventional cosmic timelines. The imagery of these interactions is both violent and cinematic. Picture spiraling arms twisting and stretching under tidal forces, streams of stars arcing gracefully across the void, and gas clouds colliding in brilliant explosions of light. Supernovae erupt as a consequence of newly formed massive stars, sending shockwaves that propagate across the galaxy and trigger further star formation. The dance of gravity is relentless and intricate, a choreography of destruction and creation that transforms chaos into order on scales that challenge comprehension. The audience can almost feel the gravitational tension, the motion of stars, and the energy of colliding clouds, each collision a brushstroke in a grand cosmic tableau. Observationally, astronomers identify past mergers through a combination of structural anomalies, kinematic signatures and chemical gradients. Streams of stars orbiting at odd angles, asymmetrical spiral arms, and pockets of chemically distinct stars all hint at ancient encounters. In this galaxy, the presence of unusually massive star clusters, uneven distribution of gas, and a central black hole that grew at exceptional speed all point toward a history of mergers that provided both fuel and gravitational scaffolding for rapid growth. These clues, when combined with simulations, suggest a narrative of repeated collisions that sculpted the galaxy into the enormous, mature structure observed today. Galactic collisions also influence the chemical evolution of the system. When two galaxies merge, their gas and stars intermingle, distributing elements and enriching regions that may have been chemically primitive. Supernovae triggered by the collisions disperse heavy elements throughout the merged system, accelerating chemical enrichment and creating the mature metallicity observed in the galaxy's stars. This process can explain, in part, why the galaxy appears chemically advanced despite its youth, with multiple generations of enrichment occurring in a compressed timeframe. Collisions, in this sense, are both destructive and generative, shaping structure, chemistry, and dynamics simultaneously. The scale of these interactions adds to the galaxy's cinematic grandeur. Each collision involves mass equivalent to billions of suns, creating ripples in spacetime that extend across tens or hundreds of thousands of light-years. Gas clouds move at hundreds of kilometers per second, stars trace complex orbits, and dark matter halos merge invisibly yet profoundly, guiding the visible components into new configurations. The audience is invited to imagine a universe in motion, a place where colossal structures collide and reshape the cosmos on scales that are almost unimaginable, with energy and force measured in degrees beyond human comprehension. Philosophically, these collisions underscore a central paradox of the universe. Destruction and creation are intertwined. Violence begets structure. Chaos gives rise to order. The galaxy's size and maturity, the central black hole's mass, and the efficiency of star formation may all be consequences of a history marked by repeated encounters, each collision a chapter in a story of accelerated evolution. The universe is revealed not as a passive backdrop but as an active participant, orchestrating interactions that drive growth and transformation in ways that defy simple prediction. By the end of this section, the audience gains a deeper understanding of the mechanisms behind the galaxy's extraordinary size. Collisions are not mere accidents. They are catalysts for accelerated evolution, reshaping the galaxy's structure, fueling star formation and enhancing chemical enrichment. The galaxy emerges as a product of both intrinsic processes and external encounters, a system whose defiance of cosmic norms is partly a result of interactions with its neighbors. These collisions provide a tangible, dynamic explanation for some of the galaxy's anomalies while reinforcing the sense of awe, complexity, and unpredictability that defines its story. In essence, galactic collisions are a key piece of the puzzle, revealing how interactions can accelerate growth, sculpt structure, and amplify the universe's capacity for creating extremes. They bridge the gap between what is expected and what is observed, showing that even in the early universe, forces beyond steady, isolated evolution can produce galaxies that challenge timelines, scale, and our very understanding of cosmic possibility. Through this lens, the galaxy is both a product of its environment and a testament to the relentless, transformative power of cosmic encounters, a living monument to the universe's ability to create grandeur from collision and chaos. In the universe, nothing grows in isolation. Galaxies, no matter how massive or luminous, are part of a larger network, constantly interacting with their surroundings. One of the most crucial components feeding their growth is the flow of cosmic gas streams, rivers of primordial hydrogen and helium stretching across intergalactic space, invisible to the naked eye, yet essential to the evolution of massive galaxies. These streams act as lifelines, funneling the raw material necessary for star formation, black hole growth, and chemical enrichment. In this colossal galaxy, the role of cosmic gas streams is not merely supportive. They are likely the engines behind its rapid accumulation of mass and its defiance of cosmic expectations. To appreciate their importance, one must first understand the environment of the early universe. At the time this galaxy formed, matter was not evenly distributed. The cosmic web, an intricate lattice of filaments and voids formed by dark matter, dictated where gas would flow and accumulate. Within these filaments, dense streams of gas flowed like veins through the universe, moving toward the gravitational wells created by dark matter halos. Galaxies that intercepted these streams could siphon off enormous amounts of gas, fueling rapid star formation and accelerating growth. For this galaxy, the presence of multiple dense streams likely provided a constant, abundant supply of material, sustaining extreme star formation rates and feeding the central black hole. Visualizing these streams is both cinematic and awe-inspiring. Imagine rivers of gas, invisible yet powerful, flowing along invisible highways carved by dark matter. They converge onto the galaxy, twisting and spiraling as gravity pulls the material inward. Upon arrival, gas clouds collide, compress, and ignite bursts of star formation, creating brilliant regions that glow across ultraviolet and infrared wavelengths. The streams themselves, though unseen, leave signatures in the galaxy's structure. Inflows of chemically pristine gas in outer regions, enhanced density in spiral arms, and turbulence in star-forming clouds. Each stream is a lifeline, a conduit through which the galaxy draws the fuel that allows it to defy the conventional timelines of cosmic evolution. The influence of cosmic gas streams extends beyond mere mass supply. They shape the galaxy's morphology, guiding the formation of spiral arms and stabilizing the disk against fragmentation. Without these flows, the galaxy might have remained small, irregular, or chaotic, struggling to form coherent structures. The streams channel angular momentum, regulate inflows to the central black hole, and maintain the delicate balance required for sustained star formation. In essence, they are both architects and enablers, sculpting the galaxy from the raw material of the universe while simultaneously sustaining its rapid growth. Observational evidence for these streams comes from spectroscopy and hydrodynamic simulations. Absorption lines in the light from background quasars reveal the presence of cold, dense gas along the line of sight, consistent with inflowing material feeding the galaxy. Simulations show that galaxies of this size in the early universe rely heavily on cold streams to achieve their mass, as mergers and internal star formation alone cannot account for the observed growth rates. In this galaxy, the combination of observed chemical abundances, extreme star formation, and structural coherence strongly suggests that cosmic gas streams were not incidental but central to its evolution. The cinematic potential of these invisible flows is immense. Imagine following a ribbon of gas as it weaves through the dark intergalactic medium, encountering other streams, merging and spiraling toward the galaxy's disk. As the gas collapses, it triggers fireworks of star formation, each burst illuminating the arms of the galaxy in brilliant color. Supernovae and stellar winds push back against the inflow, creating a dynamic interplay between supply and feedback, chaos and order. The galaxy emerges as a living system, interacting with its environment, breathing in the lifeblood of the cosmos, and transforming raw material into dazzling light and mass. The chemical implications of these streams are equally significant. Inflowing gas often has a primordial composition, largely hydrogen and helium, which dilutes enriched regions and allows for new, chemically distinct generations of stars to form. This process can explain some of the observed gradients in metallicity across the galaxy, with outer regions containing slightly less enriched material than the central bulge. The streams are not just fuel, they are conveyors of chemical diversity, influencing the galaxy's evolution and contributing to the paradoxical maturity observed at such an early cosmic epoch. Emotionally and conceptually, cosmic gas streams underscore the interconnectedness of the universe. The galaxy is not an isolated marvel. It is part of a dynamic, flowing system, drawing sustenance from the invisible networks that bind the cosmos together. Its extraordinary size, rapid star formation, and mature chemical composition are products of both internal processes and external flows, highlighting the complex interplay between environment and evolution. The universe is revealed not as a static stage but as an active participant, delivering resources and shaping outcomes on scales beyond human comprehension. Philosophically, these streams challenge our notions of isolation and self-sufficiency. The galaxy's defiance of cosmic timelines is not merely an internal triumph. It is a product of its environment, a demonstration that the universe's large-scale structure and flows can accelerate evolution in profound ways. It reminds us that the cosmos operates as an interconnected web, where events in one region influence outcomes across millions of light-years, and where invisible forces sculpt visible majesty. By the end of this section, the audience recognizes that the galaxy's growth is inseparable from its environment. Cosmic gas streams are the unseen highways carrying fuel, angular momentum and chemical material that enable the galaxy to achieve its extraordinary scale. They connect the galaxy to the broader cosmic web, illustrating that its evolution is both a local and a universal phenomenon. The narrative of the galaxy becomes one not only of internal defiance of physics and timelines but also of symbiosis with the universe, drawing life from vast, invisible currents that span intergalactic space. In essence, cosmic gas streams are both literal and symbolic lifelines. They provide the means for creation, the pathways for growth, and the invisible scaffolding that supports one of the universe's most extraordinary galaxies. Their presence explains how the galaxy could assemble mass so rapidly, sustain extreme star formation, and mature chemically at a time when most systems were still struggling to form basic structure. They remind us that even in the vast, seemingly empty stretches of the cosmos, dynamic forces are at work, shaping the evolution of galaxies in ways both subtle and extraordinary, and that the universe is far more interconnected, and far more astonishing, than we can see with the naked eye. At first glance, a galaxy may appear as a static, serene swirl of light and color, a cosmic painting frozen in time. Yet beneath the surface lies a ceaseless motion, a gravitational ballet orchestrated by the interplay of stars, gas, dark matter, and the supermassive black hole at its heart. In this colossal galaxy, the dance reaches a scale and complexity that defies comprehension. Every star, every cluster, every cloud of gas is a participant in a choreography governed by the invisible hand of gravity, tracing paths that span thousands of light-years while shaping the galaxy's structure, evolution, and destiny. Understanding this gravitational ballet is key to appreciating how such a massive and mature system could exist in the early universe. The motion of stars within the galaxy is staggering. In the spiral arms, stars orbit the center at tremendous speeds, following elliptical paths influenced not only by the visible mass of other stars and gas but also by the enormous dark matter halo that envelopes the galaxy. These orbital patterns are remarkably coherent, forming sweeping spiral arms that maintain their shape despite the frenetic activity within. Gas clouds, massive and turbulent, are drawn along these same gravitational pathways, colliding and compressing to ignite new stars in a cycle of creation that is both orderly and violent. The galaxy is a dynamic system, its evolution written in the movement of billions of stars, each acting according to universal laws yet collectively producing emergent patterns of breathtaking elegance. The central black hole adds a dramatic element to this ballet. Its gravity dominates the inner regions, forcing stars and gas into rapid orbits and occasionally flinging matter outward in energetic jets. These relativistic streams interact with surrounding gas, influencing star formation and contributing to the galaxy's overall dynamical balance. The black hole's mass, already extraordinary, ensures that the core remains a tightly regulated system, while the outer regions are free to rotate and spiral with relative independence. This contrast between the violent core and the serene outer disk creates a narrative tension, a cosmic juxtaposition that is both visually striking and scientifically profound. The interactions between stars and gas clouds are equally captivating. Collisions between clouds generate shockwaves that trigger bursts of star formation, while gravitational instabilities can stretch or compress regions of the disk, producing spiral patterns and dense clusters. Supernovae add another layer of complexity, injecting energy that can either stimulate or inhibit further star formation. In this galaxy, the rate of such events is extraordinarily high, yet the overall structure remains coherent, suggesting a delicate balance orchestrated by gravity. The result is a system that is both turbulent and stable, chaotic yet predictable on large scales, a paradox that underscores the sophistication of cosmic dynamics. Dark matter plays a silent but indispensable role in this dance. Invisible to telescopes, it provides the gravitational scaffolding that guides the motion of stars and gas, preventing the spiral arms from dispersing and stabilizing the galaxy against internal turbulence. Without this unseen mass, the extreme star formation rates and rapid growth observed in the galaxy would likely have torn it apart, leaving a chaotic, irregular system rather than the coherent spiral we see. Dark matter is the silent conductor of this ballet, shaping the trajectories of visible matter while remaining itself beyond observation, a reminder that much of the universe's complexity is hidden from view. The cinematic imagery of this gravitational ballet is staggering. Imagine sweeping across the galaxy, following individual stars as they trace luminous arcs through space, weaving through clouds of glowing gas and dust. Spiral arms twist gracefully, illuminated by clusters of newborn stars, while supernovae erupt in brilliant explosions, scattering enriched material into the interstellar medium. Dark matter, though invisible, is implied in the motion of all visible components, its presence felt in the elegance of orbital patterns and the stability of the galactic disk. The audience experiences not just a galaxy but a living system in motion, a dynamic masterpiece sculpted by forces that operate on scales far beyond human comprehension. The precision of this gravitational dance also has scientific implications. By measuring the velocities and trajectories of stars and gas clouds, astronomers can infer the distribution of mass within the galaxy, including both luminous and dark components. In this galaxy, observations reveal unexpected mass concentrations and orbital speeds, indicating a dark matter halo and central black hole far more massive than predicted. The coherence of the spiral arms, despite extreme star formation and turbulent inflows of gas, suggests that gravitational forces are finely tuned, stabilizing the system even under extraordinary conditions. This combination of observational data and theoretical modeling allows scientists to reconstruct the galaxy's formation history and understand how it could grow so large and mature so quickly. The interplay between order and chaos is a central theme of this section. Stars follow predictable orbits, yet their interactions generate emergent phenomena, spiral arms, dense clusters, star-forming regions, that are not dictated by any single star but arise from collective gravitational dynamics. Collisions, feedback, and inflows of gas introduce elements of unpredictability, yet the galaxy as a whole maintains coherence. This tension between determinism and emergence mirrors broader themes in physics and philosophy, highlighting how simple laws can produce complex, beautiful systems, and how the universe is capable of creating structures that balance chaos and order in ways that inspire both scientific inquiry and emotional awe. Emotionally, the gravitational ballet evokes a sense of wonder and humility. Observing billions of stars moving in a coordinated yet dynamic pattern across hundreds of thousands of light-years is a reminder of the universe's vastness and the intricate forces at work. The galaxy's ability to sustain extreme star formation, maintain spiral structure, and support a massive central black hole, all orchestrated by gravity, creates a narrative of cosmic elegance and power. It is a testament to the universe's capacity for organization and complexity, a living demonstration of the beauty that emerges when fundamental forces interact over unimaginable scales. By the end of this section, the audience gains a deep appreciation for the dynamic complexity of the galaxy. Gravity is not merely a static force. It is a conductor, a sculptor, and a storyteller shaping motion, structure, and evolution. The stars, gas, dark matter, and central black hole perform a cosmic ballet, each element interacting with the others to produce a system of extraordinary coherence and scale. The galaxy is alive with motion, a narrative written in trajectories, orbits, and collisions, and the gravitational ballet provides both the visual spectacle and scientific framework necessary to understand how such a massive, mature galaxy could exist in the early universe. In essence, the dance of stars and matter is the heartbeat of this galaxy. It explains the balance between turbulence and order, the rapid growth of stellar populations, and the stability of spiral structures under extreme conditions. Gravity is both the invisible hand and the storyteller, guiding the galaxy's evolution while creating cinematic patterns that awe and inspire. Through this gravitational ballet, the audience sees not only a galaxy but a living, breathing system, a masterwork of cosmic dynamics that challenges expectations, defies conventional timelines, and exemplifies the extraordinary complexity of the universe. Invisible to the eye but pervasive across the cosmos, magnetic fields thread through galaxies, shaping the motion of gas, influencing star formation, and guiding charged particles on vast journeys through space. In this colossal galaxy, magnetic forces are more than a background phenomenon. They are hidden sculptors, subtle yet powerful agents that influence structure, dynamics, and the evolution of matter on scales both enormous and intimate. While gravity commands the large-scale motions of stars and dark matter, magnetic fields operate on the level of gas clouds, cosmic rays, and stellar nurseries, adding an intricate layer of complexity to the galaxy's already extraordinary story. Magnetic fields are generated by the motion of charged particles and conductive plasma, a process known as the dynamo effect. In galaxies, these fields are amplified and maintained by the swirling motion of gas and the rotation of the disk. In a system as massive and active as this galaxy, the dynamo is extraordinarily potent, producing fields strong enough to influence the dynamics of entire molecular clouds. Gas that would otherwise collapse under gravity can be guided, stretched, or confined by magnetic tension, regulating star formation in a subtle interplay with turbulence, feedback from supernovae, and inflowing cosmic gas streams. These invisible forces act as both regulators and enhancers, shaping the galaxy's evolution in ways that remain largely hidden from direct observation. Visualizing these fields is a challenge, yet the effects they produce are tangible and cinematic. Picture vast clouds of gas swirling along invisible lines of force, twisting into filaments and sheets, collapsing into dense cores that will ignite as stars. Supernova shockwaves ripple through the medium, interacting with magnetic fields to guide the flow of matter, while cosmic rays accelerated along field lines illuminate the galaxy in radio waves detectable by sensitive instruments. The interplay between magnetism and matter creates a dynamic, textured environment, a hidden layer of order that underlies the visible beauty of stars, spirals, and nebulae. Magnetic fields are the invisible threads tying together the galaxy's intricate tapestry, influencing both microcosmic and macrocosmic processes in ways essential to understanding its evolution. The impact of magnetism on star formation is profound. Gas clouds are not uniform. They contain turbulence, density variations, and pressure imbalances. Magnetic fields act as scaffolds within these clouds, channeling inflows, stabilizing against premature collapse, and occasionally creating preferred pathways for star formation. In regions where fields are aligned with the flow of gas, star formation can proceed efficiently, producing clusters at the rapid rates observed in this galaxy. In regions where fields oppose collapse, gas may linger, delaying ignition and creating variations in stellar density across the spiral arms. The result is a galaxy where magnetic forces contribute to both coherence and diversity, regulating a balance between furious creation and structural stability. Observationally, evidence of these forces comes from polarized light and radio emissions. As charged particles spiral along magnetic field lines, they emit synchrotron radiation, revealing the structure and orientation of the underlying fields. In this galaxy, observations suggest large-scale coherence in the magnetic structure, with fields following the spiral arms and guiding the flow of gas into the central regions. This coherence is remarkable given the galaxy's extreme size and energetic environment, implying that magnetic forces are resilient and influential, capable of maintaining order amidst turbulence, starbursts, and inflowing streams from the cosmic web. The interaction between magnetic fields and cosmic gas streams is particularly intriguing. Inflowing gas carries its own magnetic signature, which can merge with or oppose the existing fields in the galactic disk. These interactions create regions of compression, twisting, and reconnection, energizing charged particles and producing turbulence that can trigger new waves of star formation. The streams themselves are guided in part by the galaxy's magnetic topology, suggesting a feedback loop where magnetism shapes inflow, which in turn reinforces and amplifies the field. In this way, magnetic forces are both responsive and directive, influencing the very material that sustains the galaxy's extraordinary growth. Magnetism also interacts with the galaxy's central black hole. Accretion disks around supermassive black holes are highly magnetized, with fields responsible for launching relativistic jets that pierce through the surrounding galaxy. These jets inject energy, influence star formation, and redistribute gas, effectively linking the black hole's activity with the broader dynamics of the galaxy. In a system already defying cosmic timelines, the presence of strong magnetic fields may have helped regulate these processes, allowing rapid growth without catastrophic disruption, stabilizing the inner regions while the outer disk continued to spiral, rotate, and produce stars. Cinematically, the concept of magnetic forces adds a layer of drama and intrigue. While gravity paints the broad strokes of motion and structure, magnetism weaves invisible lines that dictate the flow of gas, the ignition of stars, and the acceleration of cosmic rays. Imagine looking at a nebula where luminous filaments trace not just gravity's pull but the hidden currents of magnetic energy. Supernova remnants ripple along these lines, charged particles spiral in brilliant arcs, and the invisible web of magnetism subtly shapes the luminous display. This hidden dimension transforms the galaxy from a static collection of stars into a living, breathing system with layers of unseen complexity, a multidimensional dance of matter and energy. Emotionally, the existence of magnetic forces deepens the sense of wonder. They remind us that much of the universe's structure and beauty is governed by phenomena beyond human perception, forces that shape reality silently yet decisively. In this galaxy, magnetism contributes to its defiance of cosmic norms, guiding star formation, influencing inflows, and maintaining coherence across scales. It is a hidden sculptor, invisible yet indispensable, creating order out of chaos and enabling processes that seem almost miraculous given the galaxy's youth and size. By the end of this section, the audience appreciates the layered complexity of galactic evolution. Magnetic forces are not mere footnotes in the story, they are active agents shaping structure, dynamics, and growth. They regulate star formation, guide cosmic inflows, influence black hole activity, and stabilize turbulent regions, all while remaining hidden from direct sight. In this colossal galaxy, magnetism adds depth to the narrative, revealing that the forces driving cosmic evolution are diverse, interconnected, and often invisible. In essence, magnetic forces are the unseen architects of the galaxy, sculpting matter, guiding energy, and orchestrating processes that complement gravity, dark matter, and cosmic gas streams. They transform raw potential into organized motion, chaotic inflows into star-forming filaments, and violent feedback into regulated growth. Through this hidden dimension, the galaxy's extraordinary size, maturity, and dynamism are made possible, highlighting the intricate interplay of visible and invisible forces that govern the cosmos. The audience is left with an awareness that the universe's beauty is not only in what can be seen but in the invisible currents that silently shape it, making this colossal galaxy a masterpiece of both light and hidden energy. At the core of nearly every galaxy lies a paradoxical presence, a supermassive black hole, an object of such density that not even light can escape its grasp, yet whose influence extends far beyond its event horizon. In this colossal galaxy, the central black hole is not merely a passive anchor. It is an active agent, a dynamic force that shapes structure, drives growth, and regulates the extraordinary activity of the surrounding system. Its mass, already remarkable, suggests a rapid formation history that challenges conventional understanding of early universe evolution. To comprehend the story of this galaxy, one must understand the profound role of its heart of darkness. The black hole's gravitational pull dominates the inner regions of the galaxy, dictating the orbits of nearby stars and gas clouds. Matter falling toward the event horizon forms an accretion disk, heated to extreme temperatures and emitting powerful radiation across the electromagnetic spectrum. This radiation, while invisible to human eyes, influences the surrounding galaxy, regulating star formation by heating gas and driving energetic outflows. In the case of this galaxy, the black hole's growth appears closely tied to the rapid star formation observed, suggesting a symbiotic relationship. The black hole feeds from inflowing gas, while its activity helps organize and regulate the galaxy's inner dynamics. The magnitude of the black hole is staggering. Observations suggest a mass millions or even billions of times that of the Sun, placing it among the most massive known at its epoch. Such rapid accumulation of mass raises profound questions. How did it form so quickly in the early universe? Did it originate from the collapse of a massive primordial star, or through successive mergers of smaller black holes? Was it fueled by the extreme inflows of gas channeled along cosmic streams, or did exotic processes accelerate its growth? Each hypothesis challenges conventional models, pushing the limits of our understanding of black hole formation and early universe physics. The influence of the black hole extends far beyond the central parsecs. Its activity generates relativistic jets, narrow streams of charged particles traveling near the speed of light, that pierce through the galactic disk and inject energy into surrounding gas clouds. These jets can trigger star formation by compressing gas, or suppress it by heating and dispersing material. In this galaxy, the balance appears finely tuned. The black hole is active enough to energize the galaxy, yet not so violent as to disrupt its structure. This delicate equilibrium suggests a feedback mechanism operating on cosmic scales, a dialogue between darkness and light, destruction and creation, central to the galaxy's extraordinary evolution. The cinematic imagery of a supermassive black hole at work is mesmerizing. Picture a dark, invisible presence at the galaxy's center, surrounded by a glowing accretion disk, with jets of energy spiraling outward like cosmic lances. Gas clouds swirl along curved trajectories, stars orbit at breakneck speeds, and supernovae erupt nearby, adding bursts of light and energy. The black hole is both predator and guardian, consuming matter while shaping the environment, an unseen conductor orchestrating the galaxy's symphony of motion, light, and creation. The contrast between the absolute darkness of the event horizon and the surrounding brilliance of stars and gas amplifies the sense of mystery and awe, a visual metaphor for the hidden forces governing cosmic evolution. Observationally, the presence and mass of the black hole are inferred through a combination of techniques. The velocities of stars and gas in the central region reveal the gravitational influence of an enormous, compact object. X-ray and radio emissions indicate high-energy processes consistent with accretion activity and jet formation. The chemical composition and density of surrounding gas clouds suggest that inflows are being funneled into the central region, sustaining both the black hole's growth and the galaxy's ongoing star formation. Together, these data pieces paint a picture of a system in which the black hole is central to the galaxy's structure, dynamics, and energetic output. The relationship between the black hole and the galaxy also raises philosophical and conceptual questions. Traditionally, galaxies and their central black holes are thought to co-evolve over long timescales, each influencing the other in a gradual dance. Yet in this galaxy, both appear to have reached extreme states far earlier than expected. The black hole's rapid growth suggests that the galaxy's early environment was uniquely conducive to feeding and assembling such a massive object. It implies that the universe, under certain conditions, can produce cosmic structures at speeds and scales previously deemed improbable, challenging our understanding of causality, timing, and the mechanisms of cosmic evolution. Magnetic fields and cosmic gas streams further intertwine with the black hole's influence. Infalling gas follows magnetic pathways, accelerating as it spirals inward, feeding the accretion disk. Magnetic reconnection and turbulence in the inner regions can launch jets, redistribute energy, and regulate the flow of matter. These interactions link the invisible forces of magnetism with the observable dynamics of matter and radiation, creating a multidimensional interplay where the black hole is both a participant and a product of complex cosmic physics. The system becomes a nexus of forces, a confluence of gravity, magnetism, and matter, orchestrating evolution on unprecedented scales. Emotionally, the black hole evokes both fear and fascination. It is the ultimate paradox. An object defined by invisibility and destruction, yet central to the creation and organization of its host galaxy. Its presence explains how such a massive system can exist in the early universe, yet it also reminds us of the limits of human perception and understanding. The black hole is a dark, unknowable force at the heart of light and life, a cosmic enigma that both anchors and energizes the galaxy, embodying the tension between mystery and knowledge that drives scientific exploration. By the end of this section, the audience appreciates the central black hole not merely as a feature of the galaxy but as a dynamic, shaping force integral to its growth and evolution. Its mass, activity, and interaction with surrounding matter help explain the galaxy's extraordinary size, rapid star formation, and structural coherence. The narrative of the galaxy is inseparable from the story of its heart of darkness, a testament to the intertwined destinies of light and shadow, creation and consumption, order and chaos. In essence, the supermassive black hole is both architect and catalyst, a hidden engine powering the galaxy's defiance of cosmic norms. It orchestrates motion, influences structure, regulates star formation, and channels energy across immense scales. In doing so, it exemplifies the profound interconnectedness of cosmic forces, demonstrating that even the most extreme and mysterious entities in the universe are not isolated but integral to the creation of extraordinary structures. Through the lens of this black hole, the audience glimpses the delicate balance and hidden power that make the galaxy both possible and astonishing, a living monument to the dynamic, enigmatic heart of the cosmos. Stars are the engines of galaxies, transforming clouds of gas into blazing beacons of light and life, forging the elements that will one day become planets, and ultimately the building blocks of existence itself. In this colossal galaxy, star formation occurs at a rate that challenges comprehension, a furious, almost unstoppable process that illuminates both the brilliance and the chaos of the early universe. This section delves into the mechanics, implications, and spectacle of star formation in a galaxy that seems to have discovered a cosmic shortcut, assembling mass and energy at a pace far beyond what conventional models predict. The process begins with molecular clouds, vast concentrations of gas and dust that drift through the galaxy like rivers of potential. Within these clouds, density fluctuations arise due to turbulence, gravitational instability, and interactions with magnetic fields. Where a region becomes sufficiently dense, gravity takes over, pulling matter inward until nuclear fusion ignites and a new star is born. In this galaxy, the sheer abundance of gas, fed by cosmic streams and guided by magnetic forces, means that star formation is not sporadic. It is systemic, a galaxy-wide phenomenon. Clusters of stars ignite almost simultaneously across different regions, creating a spectacular tapestry of light and energy. The speed and intensity of star formation here are extraordinary. Observations suggest star formation rates hundreds of times greater than those in the Milky Way, meaning that thousands of massive stars could be forming every year. These stars, some dozens of times the mass of the Sun, live fast and die young, detonating as supernovae that seed the surrounding gas with heavier elements. Each generation of stars contributes to chemical enrichment, building a mature metallicity far earlier than expected for a galaxy of this age. This accelerated cycle of birth and death explains much of the galaxy's paradoxical maturity, illustrating how extreme environments can compress the evolutionary timeline. The cinematic imagery of this process is breathtaking. Picture dense, glowing clouds swirling through spiral arms, collapsing under the combined forces of gravity and magnetic fields. Bursts of star formation ignite like fireworks, illuminating dust and gas in brilliant colors spanning the spectrum. Supernovae erupt with violent brilliance, scattering enriched material into neighboring clouds, triggering new waves of star birth. The galaxy is alive with light, motion, and energy, a living laboratory where matter transforms continuously, revealing both the beauty and the chaos inherent in cosmic creation. The interaction between star formation and feedback processes is critical to understanding the galaxy's extraordinary growth. Massive stars inject energy into their surroundings through stellar winds, radiation, and supernova explosions. In typical galaxies, this feedback can disrupt gas clouds, slowing star formation and regulating growth. Yet in this galaxy, the feedback appears balanced, energetic enough to enrich and energize the environment, but not so overwhelming as to halt the creation of new stars. This delicate equilibrium allows the galaxy to maintain high star formation rates without fragmenting or dissipating, a remarkable feat that underscores the efficiency and resilience of cosmic processes at extreme scales. Chemical enrichment is another vital consequence of star formation. Each generation of massive stars produces heavier elements in their cores, which are then dispersed into the interstellar medium upon death. These elements, carbon, oxygen, iron, and beyond, become the raw material for future stars, planets, and potentially life. In this galaxy, the accelerated pace of star formation ensures rapid enrichment, explaining why even outer regions contain stars with metallicities comparable to galaxies much older in cosmic time. The chemical fingerprints left behind offer astronomers clues to the galaxy's history, revealing a fast-paced cycle of creation that defies expectations and challenges conventional models of early universe evolution. Star formation is not uniform across the galaxy. Regions near the center, influenced by the gravitational pull of the supermassive black hole, experience intense bursts of activity, with gas funneled inward by cosmic streams and guided by magnetic fields. Spiral arms act as stellar nurseries, where density waves compress gas and ignite sequential star formation. Even the outer regions, fed by infalling primordial gas, show pockets of activity, contributing to the overall mass and luminosity of the system. This diversity in star-forming environments creates a galaxy that is both complex and coherent, a mosaic of creation operating on multiple scales simultaneously. The scale of star formation also amplifies the visual and emotional impact. The combined light of billions of newly formed stars can rival entire smaller galaxies, creating a glow that illuminates the surrounding intergalactic medium. Supernova shockwaves ripple through the galaxy, stirring turbulence, triggering further star formation, and scattering the seeds of chemical enrichment. The interplay of light, motion, and energy creates a narrative of continuous creation and destruction, a visual story that mirrors the scientific processes shaping the galaxy's evolution. Philosophically, the galaxy's star formation challenges notions of temporal constraint and cosmic moderation. It demonstrates that the universe can operate at extremes, compressing processes typically measured in billions of years into a fraction of that time. The galaxy becomes a testament to the power of environmental factors: dense gas, magnetic guidance, dark matter scaffolding, and inflowing streams, in accelerating cosmic evolution. It highlights the universe's capacity for both creativity and efficiency, revealing that even in its youth, it was capable of producing structures of extraordinary scale, luminosity, and chemical complexity. By the end of this section, the audience gains a profound appreciation for the galaxy as a cosmic forge, where stars are born in extraordinary numbers, chemical elements are rapidly produced and distributed, and energy flows dynamically through the system. Star formation is not merely a process, it is a defining feature of the galaxy, shaping its structure, composition, and luminosity, and enabling it to exist as a mature, massive system in a young universe. In essence, the galaxy's furious star formation is both spectacle and mechanism, a continuous process of creation and enrichment that fuels growth, illuminates the cosmos, and defies temporal expectations. It illustrates the interconnectedness of cosmic forces: gravity, magnetic fields, dark matter, black hole activity, and inflowing gas streams, working in concert to produce a system that is astonishing in scale, complexity, and beauty. The audience is left with an awareness that this galaxy is not static but alive, a dynamic forge of stars whose brilliance and productivity reveal the extraordinary possibilities of the universe in its formative epochs. The discovery of this colossal galaxy sends ripples across the field of astrophysics, forcing a re-evaluation of what we believe the early universe was capable of producing. Its sheer size, accelerated star formation, and mature chemical composition challenge the conventional timelines of galaxy formation, suggesting that the cosmos may have been far more dynamic, efficient, and audacious than previously imagined. No longer can astronomers assume that early galaxies were uniformly small, chaotic, and primitive. This galaxy acts as a cosmic benchmark, a tangible reminder that extraordinary structures could form under specific conditions, defying expectations and expanding the limits of possibility. The implications extend to our understanding of dark matter, cosmic gas flows, and the processes that regulate star formation. The galaxy's rapid assembly hints at unusually dense regions of dark matter that could have funneled gas more efficiently, accelerating growth in a way previously considered improbable. Cosmic gas streams appear to have delivered the raw material necessary to fuel this accelerated evolution, while magnetic forces and gravitational dynamics maintain coherence amidst extreme activity. Each component, from the invisible scaffolding of dark matter to the turbulent birth of billions of stars, must be reconsidered in light of a system that matured far ahead of its cosmic peers. Furthermore, the supermassive black hole at the galaxy's core forces a rethink of black hole formation and coevolution with host galaxies. Its enormous mass in such an early epoch suggests either extraordinarily rapid growth or alternative formation mechanisms that challenge existing models. The feedback processes linking the black hole, star formation, and galactic structure demonstrate a level of complexity that underscores how intertwined these cosmic phenomena are, and how flexible the universe can be when conditions are extreme. This discovery also has philosophical implications. It confronts humanity with the vastness, complexity and unpredictability of the universe, highlighting that our models and assumptions are always provisional. The early universe, rather than being a uniform, incremental environment, could produce giants that break the rules, reminding us that the cosmos operates on scales and under conditions that stretch imagination. It invites wonder, humility, and a recognition that even in a universe governed by physical laws, creativity and exception exist on a cosmic scale. Finally, this galaxy acts as a guidepost for future exploration. If such massive, mature systems existed in the early universe, many more may await discovery, hidden among the faint light of distant space. Each new observation will refine our understanding of cosmic evolution, galaxy formation, and the interplay between visible and invisible forces. In revealing a universe capable of producing the extraordinary, this galaxy does more than inspire awe. It reshapes the questions we ask, the models we build, and the scope of what we dare to imagine. In essence, the galaxy redefines cosmic limits. It challenges timelines, illuminates hidden processes, and stands as a testament to the universe's capacity for rapid, extreme, and beautiful creation. Its existence transforms our understanding of early cosmic history, forcing a reconsideration of what is possible and inspiring a deeper exploration of the universe's mysteries.